questions on it? I mean, we ended with the McNamar's test, right? Got some notes here.
Yes.
We can just start it down.
Okay, now recall we're looking at a discrete distribution, right? It have many categories, and at the moment we picked on two categories of interest. Okay, we talked about one category, right? That would just be the binomial. That category is success, everything else is failure. So we've done that. And now how about two categories? Like if you take a poll, you might be interested in maybe it's candidates for political office, and you might want to know the difference between the Democrat and the Republican, and just ignore everyone else. So you have two categories of interest. So then we talked about estimation and confidence intervals last time, right? So we have it. There it is. There's the estimate. Of course, the difference in proportions. What else could it be? There's a standard error, right? We talked about that last time. And then the confidence interval would be the standard error times the critical value, plus or minus the estimate. Any questions on that? That's straightforward. Okay, so that's taken care of. And then we start talking about testing. You could set up a test like this. This would be like if you put the hats on the piece here, that would be a wall type test. But most often we design our test statistic under H0. And under H0, the p's are equal, so you could just get rid of that square difference here, right? And when we do that, and it comes down to that. I don't know why I crossed that out for some reason in the lecture, but then that thing would be 0. Well, that's a standard, asymptotically, that's standard normal 0, 1, and if you square a standard normal 0, 1, you get a chi-square with 1 degree of freedom. And so if we do that, when the dust settles, you come down with O1 minus O2 squared over O1 plus O2. And this is referred to as McNamar's test. Okay? Now, McNamar's test has a neat application. Actually, that's the way I'm used to it. And that's testing for significant change. So this is a neat application of McNamar's test. Sometimes in a problem, it takes a while to set it up. But here's an interesting problem. Okay, you have a debate between two candidates, say A and B. Okay, and you hold the debate in a large room, and many people attend, and then you poll the people before. Suppose it's for a political office. So you poll the people before if they're for A or for B. And then after the debate, you re-poll them and ask them if they're for A or for B. Okay? And of course, what you're interested in is change, right? And then given change, you might be interested in the one, people moving to more to the one than to the other. So it's a neat problem, it happens in applications. I just ran in a clinical study. They had to answer on a scale, and before, it's like everyone was at the far right, and after, it's like the mass is spread out all over the place. So I did it on before and after on that, it turned out fairly good. The FDA should find out. Well, certainly you would put this into a contingency table, right? So this would be after, and this would be before. So if a person liked A before and then still liked A, he'd be in this category, right? And if he liked A but then he switched to B, he would be in this category. If he liked B and then switched to A, he'd be in this category. And if he's stuck in B, he's in this category. Okay? So you're only interested in the off diagonal, right? It's interesting to test. So this is P11, P12, P21, P22. Okay, so that's our four categories, and I'm interested in just actually this diagonal difference. Okay, so the null hypothesis is sort of interesting. It's like conditional. Let's do it one side. That's really your hypotheses, okay? The two side would be, the null would be, there is no change one way or the other. The amount of change is the same. That's probably better. Then let's do a one-sided one. That would be one each other. Then in symbols, what is this? Well, that means P12 is equal to P21. There could be a lot of change, but it all washed out. No one really won. It's like winning in debate too. You can think of that. But we do have that before, so it's not quite a debate. And then here P12 dominates things. The flow has been familiar. Then it's like our setup, right? We only have two categories of interest. In the test statistic, we just use maximums. Yes.
I mean, shouldn't the alternate hypothesis be not equal to?
It could be too. Right. We're doing it on one side. A to B is more likely.
Well, if it's one-sided, wouldn't the hypothesis not be less than or equal?
No, it's more likely. Got the boxes around everything. Then you could have two sides. That's the case if you maximum numbers. And then the p-value is I² is maximum. So it would be, you put the subscripts in if you wanted to. Okay. And then the p-value, actually, for a one-sided test, you would do maximum R's. This would be I²1, where we would do the first I². And then you run it. This is one side. Now you gotta be careful, you're squaring that difference, so you have to know that. I should have wrote the difference the other way, right? No, that's right. Look at it first. If it's positive, go ahead. If it's negative, uh-oh, you better switch to two sides. You might want to do two sides and do a one side completely. I think that's what I end up doing. Then you don't divide. But you might make it one side. That's what most stats are. Okay? Let's just look at an example. I think it would have been interesting to see this on the first debate between Romney and Obama. Romney clearly was one in the debate. Obama is kind of the elder Bush. When Bush was debating, in the middle of the debate, he was looking at his watch. Why am I here? Yeah. Whatever. Of course, I've been doing the same thing. Okay, another interesting debate on was Nixon and Kennedy. Their first debate, because Kennedy knew what he was doing. He had cosmetics and everything. In those days, no TV, okay, you had these cosmetics and everything. He had a good-looking face for the camera. Nixon didn't. Nixon looked like he needed a shave. Kennedy really paid right. He wanted to do it. Okay. Well, I have some data here. I just think of it. Oh, okay. So in this example, let's say this, we have this poll. This is before, and this is after, right? So before, 30 were for A, and 30 stuck with A. 25 were for B, and 25 stuck with A. After, 15 switched from A to B, and only 5 switched from B to A. Okay, of course, this looks like, this favors one alternative. Again, the test statistic is easy, it's just the difference in these O's squared, right? Divided by their sum. So the difference is 15 minus 5 or 10, 10 squared is 100. And 15 plus 5 is 20, so it's 5. Okay, then if you look at the probability of chi-squared one random variable is greater than 5, it's 0.0253. Then for a one-sided test, we want to divide that by 2, so it's only 0.02. Okay. I can't get out, but I can at least show that. I'll have to call IT. I don't have any trouble upstairs. Let's do this one. Now it's time for Joe's. The p-value would be this. This is called p-value, so we can divide by 2 later. It's just 1 minus probability of chi-squared, right? Remember, it's continuous, so there's no subtraction from 1. So you have 5 in here, and then you have to have the degrees of freedom, which is 1. And then this is our p-val, okay? Just like I have it. And then this should be our observed. Okay, any questions on that? Actually, the beauty of this test is, it's like conditionally, you ruled out the main diagonal, and conditionally, you can test this with a binomial distribution, where the probability of success is 1/2. See, under H0, P12 is equal to P21, so it's like half the time you'll go from A to B, and half the time you'll go from B to A. See, you rule out sticking. So there's an exact test. You can do an exact binomial test, and the one good reference book, I'm sure I have it in somewhere, the book by Holder and Wolf. P-value for the exact test would be, there you have to go back to the number of successes, which would be 10, it's the difference, right? Too many S's here, successes. Check. We call it T, total successes. T is to the large. And then the p-value for this is the probability that a binomial is 0.1 2 plus 0.21, that's the number of 6 trials, okay? You just ignore that main diagonal. P is 1/2, and you determine the observed T. Any questions on that? That would be the p-value. Now you have to remember to subtract when you do the complements. So our p-values would be, that would be the one side. It would be 1 minus p bar minimum, right? And that would be 20. Oh, you don't do the difference. Sorry. Let me back up on this. $15. So it's pretty close. We got what? 0.0126 and exact is 22. Any questions on that? I think for the class, let's just do the chi-squared approximation. You can get that from the chi-squared table. Okay, any questions on that? Well, the last thing we have to do this week, it's like we went from one category, now we have 2 categories of interest. How about all categories? And sometimes that is of interest, okay? Sometimes you have a definite distribution in mind for how the category should have filled in, and that's what you want to test. Okay? Now, sometimes you know the specific distribution, and another time you just know the form. Like it should be binomial, it should be Poisson. The second way, then you'll have to estimate a parameter. But the test is very simple. It's one of the oldest tests known to man. It's just the goodness of fit test. Your observed frequencies and your null hypotheses tells you what the expected should be. In the second case, you'll have to estimate. And then you just look at the difference. It's O minus E squared, right? Divide by EE, and then just add them all up. So again, it's discrete, right? Okay, categories. And so, the distribution of X is S, right? J, and then we have these P's, right? And they have to add up to 1. And H naught is a distribution of X is, and then the alternative is actually just not, it's not H naught. I don't know what it is, but it's not H naught. Okay? And then the test is a possible chi-squared root is a fit test. We just reform the E's. X of J will be the expected value under H naught. That X is equal to J. Back up anyway, so chi-squared root is a fit test. So we observe a sample, right, size n, but they can only be one of those, each is one of those K categories, so we just make a table, right? We make a table. These are the observed frequencies we talked about last time. They have to add up to n. Okay? And then we form the expected frequencies. So this would be the expected value. Dj would be the expected value of Oj under H naught. So this would be n times, and it would be the distribution we specify. So you might have P naught. The H naught's going to be, you have to specify these for H naught. So that's what you would expect under H naught, and then the test statistic is just O minus J. The O minus E. Understand that? Okay. And then you reject H naught. Chi-squared is too large. What else? And then the p-value is, and it's k minus 1 degrees of freedom, greater than the observed chi-squared. Okay.
There.
Okay, let's just do a simple one, let's just throw a die. Let's have the computer throw, let's make it a fair die. It'll throw the fair die, I don't know, let's say 600 times, so the expected frequencies would be 100. And it's simple to do. So I'm just make the cats 1 to 6. Okay. Here's my die. And then let's sample 600 times on this placement. And that'll be, we'll call them OBS. Right? Sample from cats 600 times, not 6,000. So there, the computer was really busy. Start off with 3 deuces. Wow. The die is crooked. So there's our observed frequencies, right? And then of course we table them right away. So there's our observed frequencies. Now, in this case, the hypotheses of interest is the die is fair. And see, the alternative is the die is not. And of course, that means all the p's are 1/6, right? And then the alternative is it'd be at least 2 p's not 1/6. You just say at least 1. Any questions on that? And the expected frequency would be under H naught, right? It would just be 600 times 1/6. Right? That's what you specify under H naught. PJ is 1/6. So this is 100. Then you just look at the differences, square, add them up. Well, you get to standardize the differences, okay? And then, let's just do staff. And just add them up. So this is what. It doesn't actually look too bad, right? You're down a bit on the 4s. Maybe you're up a bit on, well, you're really up on 3s, right? 15 from the 4. Now you expect some discrepancies, okay? You're not like Mendel in these experiments, right? So you expect some discrepancies. If you see all 100s, then you conclude immediately that the data is fixed. So the stat score for, we have 5 degrees of freedom in the problem. And for the chi-square, remember, the mean is the number of degrees of freedom. You expect 5, and you observe 4. You're not going to be rejecting H naught. Okay? You can determine the p-value. The p-value would be 1 minus, right, p chi-squared. And stats 4.84, right? And we have 5 degrees of freedom, k minus 1. So the p-value is about 3 quarters. I mean,
Quick question, when you were making that observed sample, you had replaced equals t as one of the arguments for
Oh, yeah,
sample, what is that? I understand what we're, we always have 6 to choose, but what does the big T mean?
True.
We do the same thing with
True as opposed
What's
to
it-
false.
each row
Okay.
from the top.
Okay.
If you have replaced equal false. Now again, we could do, we did reject H naught, so you might start looking at where you see the discrepancies, so you might be looking at 3s. You have to be very careful on the, you're going to start running into a multiple comparison problem pretty quickly. You could start. And you know, you can look at confidence interval, probability of 3. And this goes from 600, and you got 3, 13, 600. You can talk about multiple comparison problem. I don't think I'm going to talk about it. You do have to be careful making the volumes. Here, I don't think you'd be doing like a math.
Okay.
But you might be interested in this. Okay, the second form is, the second setup, the form is known, that's it. You don't know the exact distribution. And there's a great example in the book, I found this data set. I couldn't believe it. It's an old data set. The birth rate of males to Swedish ministers. So it's around the turn of the century, it might be late 1800s. And they looked at the first 7 children. So that's the number of trials, 7 children. And then a success in this study was a boy. They wanted to see, discuss the distribution of males in the first 7 children.
Example 3, 1.
And so here we have the observed frequencies. Six of the ministers had no sons. So these guys had, 7 daughters, right? 13 of them had 7 sons. 362 of them had 3 sons. So here, the form might be the thing of interest, and the form would be it's binomial. Each child is a trial, and it's, you had a couple kids, it's a trial, right? Each child is a trial, and it's either a boy or a girl, and we have 7 trials, okay, and up to 7, see what happens afterwards. But they must have 7 kids to get into the experiment. And we're going to see if it's binomial. Success is either or. There's the 7 trials and there's success and failure. So we just want to see if the form is binomial. So in this case, H naught is distribution is binomial. So you do the experiment, and then in this case is 1334. Okay, so then you're gonna then you get the observed frequencies. That's what you got. You've got the abilities. Now we just need the expected frequencies. EJ would be what? It would be n, and it's supposed to be binomial. So it's probability of binomial. These 7 trials, right? Better use them. And then what's the probability of success? Is equal to J. And I can even write down the formula if I want to. So I'm all set, but it's not specified, right? Well, there is a goodness of fit test for this. We just, we estimate P by, actually the maximum likelihood estimate usually used, but it's just the intuitive estimate. And it's the number of successes over the total number of trials. Put down the total number of trials, I think you get an idea of what's going on. It's 1,334, and they each had 7 trials. So that's the number of trials in this experiment. It's that product, okay? And then what are the successes? Well, 6 had 0 successes. 57 had 1 success. And turn 6 had 2 successes. Turn 62 had 3 successes. And turn 65 had 4 successes. Okay, any questions on that? It's a little bit tricky, right? But that would be the probability of success. Yes. And I don't know if you read the piece of book, but it comes out in 1 If you before we started screwing around with things, pun intended, but, that was the probability of a milk child was about 15%. This milk child is weaker, tend to die more frequently. Female children around birth, shortly thereafter. Infant mortality. So nature accounts for that by having more sons, more than daughters. No, we messed it up. The son was good. Hate to see what happens in 100 years. Okay, but now you're set, okay, and you use it for your freedom to write matters. This is the question. You use it for your freedom. But going back to this thing, you just plug in that. So you could do that in R. Just have to have data. If you're working with R, you put data in this way. Well, you have to put data in. I'm going to get an example. Coming back to the tell me two. It's not a nice report. Okay, so there's our observed frequencies, right? And then we need distribution. We could just use that we have. So we need D, right? And make sure you get to 0. 0 to 7, right? And then N is 7, and P is at 514. Ooh, it's called P. There's the P's. Okay? And then we need the E's, right? The E's would just be, what we said, well, it's N. It's 1334, but gotta be careful. It's not the total number of trials. There's the expected frequencies, and there's the observed, and then our test. We got 8 categories. Be careful. There's 8 categories. So we have, we start with 7 degrees of freedom, and then we had to make one estimate, so we're down to 6 degrees of freedom. And that's almost right on the nose, right? The expected value of pi squared would be 6, and it's 5.977. And sort of neat. Any questions on that?
Yeah, there's some degrees of freedom correction. I squared. I always, I keep on looking at you, right? Not like 6 squared or sums of squared
You
multiplications.
start the number of categories, which is 8 here, okay? 0 through 7. So, and then you lose one category because once I know n, if you give me all categories but one, I know the last one. So those numbers aren't that free. Okay, so you're down to k minus 1 at the beginning. Then you made an estimate. You had to estimate p here. You use the freedom for that. And so it's k minus 2. So it's sort of neat, right? You could try it with a half. That would be the naive one. See if it's. Okay, let's do it with the half. That's the naive one, and that is not an estimate. That's not an estimate. That's really the first way. That's the naive answer to this one. And actually, it's pretty close to what it is now. That's the change. So I'm just going to erase this. It's kind of dangerous. So you'd reject that. It's 13.29. Here's the p-value, right? It's 1 minus p chi is 2 staff. And we have, in this case, we start with 8 categories, and we only use 1 degree. So you go in estimate. So it's almost significant for 5%. Any questions on that? That's sort of nice. Carson's big thing, but not big enough. Wrong. These convenient. Okay, so now we're going to start with continuous data. So any questions on that? So we've done the discrete case, so now we're going to look at the one sample continuous case. Now, in the discrete case, there are only certain categories, okay? And then we're interested in that. There was no question about the distribution of the sample for a discrete case. You know, this is the distribution, right? There's no other to think about. In a continuous case, that's not true, right? What is the distribution? Well, we have some population generating the data. We don't know the population. Right? There's no data or just measurements. Okay, so there's no convenient categories to stuff them into. But of course, what you do is you make up some categories, so you at least get a sense of the distribution, right? I mean, what you'd want to do here, if you were really going to do this as some sort of report, you'd probably make a history of it, right? A picture of that distribution. You might have a distribution in this case given, but you'd also have a picture. And if I give you a bunch of measurements, you want to do the same thing. So you want to turn those measurements into a picture. It would be a distribution. In this case, the picture would be the distribution. Again, you might merge some categories out here. And that, in that sense, is still not the same problem. so you make categories, right? And then you might get some summary statistics. And you're trying to describe the data. Which you might also just. So let's talk a little bit about that today. Things will go faster if you give me the answers. So how do you make the categories? Pardon me?
Standard deviation.
Yeah, you could do that, but I don't want, I want to do it non-parametrically, so I'm just going to make up some categories. And, then if I don't like the picture at the end, I just want to change the categories. So I said change the categories, that means you have to redo it, so you don't do that. So the easiest way is to just do a stem leaf plot. Right? So you want stems, then you want to put the data will be the leaves, and you want to put the leaves on the stems. If you do it by hand, that's what you want to do. For stupid glitch in the computer today, it's not. But it's. I'll just make a simple data set and then put it. I'll just go for it. It's just that 20 observations. So there's our observations. I have 20 measurements. And then to get an idea of what's going on, just make a stem leaf plot. And then just take simple stems. How about tens? That's what I would do first. I got a 30, a 33. I got a 90, right? So just make stems. So how do you do it? Stem, right? Stem. You could do it by hand. Just to get an idea of what's going on. Right on the screen. So there are my categories. I just make some nice categories. And then I just apply the leads. It's 51, 56, 37. And 54, 92, 15. Okay, any question on that? Then when I'm done, I'll have, if I do it neatly on tablet paper, I can just rotate it 90 degrees and I have a history. You might want to tap me on the board. That's all I have to do. So then when you do it with the computer, then what did the computer do? It merged them.
all the tunes.
You can ask for help and figure it out. I like mine better, that's not dumb, he doesn't even have the outliner. That 2 is 92. So these are what, probably 20s and
Done by
30s.
2, the 20,
Right?
by 10.
Yeah, it's 37. So these are 20s and 30s, these are 40s and, yeah, 40s and 50s, 60s and 70s, 80s. Yeah, I like it. Histogram had mine. And there's the outline. Now, if you don't like these groupings, of course, you'll get a different picture. So there's no the picture. That's sort of a nice picture. I'll go with that. We only have 20 observations. Okay. Now, let's look at some descriptive statistics. I'd like to talk about the 5 basic descriptive statistics. They're very simple. They're very simple to explain to people. The min and the max, you always want to talk about the range of the data. These measurements are not robust. Really. That outlier really makes a turkey out of the range. There's nothing down 92. I can sort the data. Let's see. 64 is the next group. So my range is, my data goes from 30 to 92, but if you're trying to describe data to people, I think you want to say the range. Then how about like the middle data point? So half the data is less than that, half the data is greater than that. That's the median, right? You always want to give the median to people. It's very descriptive. It doesn't change. You know, if you're living in a neighborhood, you might want to know the median cost of a house in your neighborhood to see if you're above the median or below the median. Are you in the upper 50% or the lower 50%? Okay. And the median is really robust to outliers, right? So that's the middle order data point. Which is called Q2. It's the black gentleman called Phil hat. Called Phil hat. That's just the median of your data. So 50% of the data is less than equal to theta hat. 50% is greater than equal. And there's a rule if you have a huge data set. And this would be the median, right? In this case, n is 5. You know, you remember the rule. So if n is odd, then the median is
The middle piece.
in fact, let's use this notation today. We'll keep using it. What does this notation mean? This is the ordered data points, and the median is n plus 1 over 2, which in this case would be 5 plus 1 over 2 or 3. It's the third ordered data point. You put the data in order, and you pick out the third one. So it's 14. Any questions on that? That's new notation, but we'll just use it from now on. This is your second choice in stat. Do a little bit of sugar. I'm not doing notation. I make things easy, not difficult. 10 is even. Here's a big data set that is even versus not. Middle data point, you just take the average of the two. And then the median is 1.5. And you can use this notation. The number 2 would be an median, so it's, and then you just go up to the next one. So in this case, it would be, well, 16. .5 is a median, so that cuts the other. What's the next two? Times up. What's the next mean?
Mean.
No, you don't want the mean. The mean's not descriptive.
And then that.
It's like the same here, but. Here's my new data set I had. Oh, that means what? 450,000. And the median is 450. This class we use robust statistics, and as much as possible. The mean is not very descriptive. Although you might want to talk about the mean, and often you do have it in there, but you have to be careful with it. If I give you that range of houses in your neighborhood, that data, you don't want me to use the mean because in my data set, I have, a millionaire a few blocks over has a house that's worth several million. And we're not in LA, so that's a pretty expensive house. It's going to swamp your rest. Okay. Oh, so what's the next two? Yeah. Quartiles, yeah. That's what- The median works great, just apply it two more times. Take the median of the lower half, the median of the upper half. Those are the quartiles, that's how I'll talk about it. And that'll be our 5 basic descriptors. That's what we're really talking about.